Now we will go to our case 1, where we have the inner cylinder and an outer cylinder. That's the same, we have discussed it all around. Outer cylinder is provided with an velocity omega, so it's moving with the velocity r omega. Its radius is r, inner radius is small r, and the width is gap is b at a b distance. Velocity we have assumed to be linear, varying linearly, xb. Now we have some assumptions here. We are taking incompressible Newtonian fluid. Incompressible Newtonian fluid. So we have another answer like incompressible. So Vz is not varying in z direction. T naught we are taking at inner cylinder temperature. This is T naught. Tb we are taking as outer cylinder temperature. Now temperature is a function of R alone, or in this case, since we have taken Cartesian coordinate system, so at steady state it is a function of X alone. We're not taking R here. Omega is the velocity of outer cylinder. It's actually R omega. Velocity of outer cylinder. And since R is very greater than P, the gap, curvature effects can be neglected. We already know, we have discussed before, Vx is 0, Vy is 0, and the velocity profile which we are expecting is this. Now how would the temperature vary? It's pretty obvious that the temperature due to higher friction will be here and will vary like this and will be lowest here. So that's T naught and Tb, where Tb is greater than T naught and temperature is a function of X alone. Now we can go back to our shell energy equations. That will be rate of combined energy flux, E in minus rate of E out plus rate of work done by external forces plus rate of energy production. Rate of energy production. Now we know that this term will be 0. Why? Because there is no role of gravity or pressure. This term will be 0 because only heat produced is by viscous source, and we have already counted that before. We have already accounted for that before. Where we did that? This pi dot v. This is viscous heat flux. So these two terms will be 0 itself. So that makes it even better because the shell we are having is of thickness delta x, the width is w, and the length is L. Now we will take an energy flux balance. That is going to be definitely what? WL into combined energy flux at x minus WL into combined energy flux at x plus delta x. This is 0. We'll rearrange it a little bit. E at x, and now we will divide it with what? We will divide it with WL delta x. That will make it WL will get cancelled out, so that's pretty obvious. Now it will be E at x plus delta x minus E at x upon delta x is equal to 0. This is a definition of first order derivative. So that is nothing but dEx upon me dx, which is equal to 0. Now we will integrate this to get a constant. So if we integrate it, that's pretty simple, that E is equal to C1, or rather Ex is equal to C1. We got one equation. Now we know E is equal to half rho V square plus rho U into internal energy plus pi dot V, and we are taking in x direction, so that x plus Qx. Now we can open this up, pi Vx, that's going to be pi xx into Vx, pi xy into Vy plus pi xz into Vz. Now we know Vx is 0, Vy is 0, so this comes out to be 0. We are left with pi xz into Vz. Now what's pi xz? That's going to be nothing but tau xz, and that's into Vz. Tau xz can be written as minus mu dou Vx by dou Z plus dou Vz by dou X into Vz. Now we know Vx is 0, so this comes out to be 0 as well. So this is minus mu dVz by dx into Vz. This is what we will get. And we know Vz, we also already know what is dVz by dx, because we know the velocity profile. We did it before. That's going to be nothing but Vb upon me b. We can put it right here. That's minus mu Vb upon b into Vz. We solved for this part. Now we can go for Qx. We know Qx is nothing but minus k dt by dx. Now suppose that we will have to integrate this, or rather let's put it here. E is equal to 1 by 2 rho v square plus rho u cap, it's Vx here also Vx, plus pi dot V came out to be minus mu Vb upon b into Vz minus k dt upon dx. Now we know V is 0, Vx is 0, so this will be further simplified. E is nothing but minus k dt by dx minus mu Vb upon b into Vz. We got this equation at first. Now we already know Vz is nothing but Vb into x by b, so we'll put the value of Vz here. So that's if k is equal to minus k dt dx minus mu Vb by b, and Vz came out to be Vb x by b. So E is minus k dt upon dx minus mu, so this Vb, so that's Vb upon me b whole square into x. We got the particular value of energy flux. Now we need to get what is the value of C1. We know this is Ex, and Ex we already know is C1. So this is minus k dt upon dx minus mu Vb square upon me b square into x. We got the value of C1. Now we need to find C2. So suppose that we took k dt by dx here. K dt by dx is equal to minus mu Vb upon b whole square and into x minus C1. We will get dt by dx is equal to minus mu upon k Vb upon b whole square into x minus C1 upon k. Now if we were to integrate this, we will get a temperature profile. Tx is equal to minus mu, obviously this is going to be 2k, this is going to be Vb upon b square x square minus C1k into x plus C2. Now this is our basic temperature profile, because we will use it in for case 2, case 3 and case 1, both cases 1, 2, 3. This temperature profile is very important. Now we have to get the value of C1 and C2, so we'll use the boundary conditions. So for boundary condition 1, We know that at x is equal to 0, T is equal to T naught, and second that at x is equal to B, T is going to be TB. We got these boundary conditions from here, that at x this distance was B, so at x is equal to 0 this is T naught, and x is equal to B this is TB. Now we will put these equations. First of all, let's assume this is at x is equal to 0, and when you will put x is equal to 0, you will get T naught is equal to C2. You got the value of C2. Now let's put x is equal to B, second boundary condition. So that would be TB is equal to minus 2k VB upon B whole square B square minus C1 upon K plus T naught. We can write this here, TB minus T naught is equal to minus mu upon K VB upon B square into B square into B square, and that's going to be into 1 by 2. I guess it's B here, so it's B into B square as well. Now minus C1 upon K into B. This is what we have got. Now that is TB minus T naught. We take 1 by K as common. We will get equation as minus mu VB square, and that would be 2 upon 2 minus C1 upon K, and we are taking B common. B. That's going to be with minus C1. So C1, if we try to get the value of C1, that will come out to be minus mu VB square upon 2 minus K TB minus T naught. Here it's B, TB minus T naught upon B. So we got the value of C1 as well. We got the value of C1. Now we need to put C1 and C2 to get the temperature profile. So if we put that, we will get Tx is equal to 1 by 2 mu VB square upon K TB minus T naught x by B 1 minus x by B plus x by B, obviously, and it's not going to be Tx, rather Tx here would be T minus T naught upon TB minus T naught. So we have received the temperature profile for the first case. Now we know one more thing. We need to know about a number, which is Brinkman number. What is a Brinkman number, first of all? So Brinkman number is nothing but is a ratio of viscous heat dissipation. Viscous dissipation upon conduction heat transfer. So suppose if Brinkham number is greater than 1, that basically means viscous is dominating. Viscous dissipation dominates. And if it's less than 1, then conduction heat transfer dominates. Now this is significance of the Brinkman number. What is the Brinkman number? So Brinkman number, it can be written as U VB square upon K TB minus T naught. So this makes it all for case 1. Now we'll go on.
Now moving on to case 2. Here we again have some basic assumptions. Our assumption 1 is incompressible Newtonian fluid. Now our assumption 2 is outer cylinder have temperature T naught. and our inner cylinder temperature is also T naught. And at steady state, T is a function of R. As we can see, this is a similar case as of previous one, but only boundary conditions have changed. So as we have our temperature profile, which is minus mu by K VB upon B x square upon 2 minus C1 upon K into x plus C2. Now putting our boundary conditions, that is at x equal to 0, T is equal to T naught, and our second boundary condition, that is at x equal to B, T is equal to T naught. Now this is only mathematics, so solving this, T naught is C2 as T naught equal to minus mu upon K VB upon B whole square, sorry this is also whole square, to B square upon 2 minus C1 upon K into B plus T naught. Now solving further, our equation upon K VB upon B whole square into B square upon 2. B and B will cancel out from both sides and K will also get cancelled. So we will get T equal to minus mu upon K VB upon B whole square x square upon 2 plus mu VB square upon 2B into 1 upon K into x plus T naught. Here from here we got C1 equal to minus mu upon mu VB square upon 2B. After rearranging our equation, we get T minus T naught equal to 1 by 2 mu VB square upon K into x by B into 1 minus xB. Now our case 3. It will be same case, but again we will have some different boundary conditions. Our boundary condition 1 will be that at x equal to 0, T equal to T naught, and our boundary condition second will be that at x equal to B, our Qx will be 0. So again solving the basic mathematics, we have not equal to C2. Now dt by dx equal to minus mu by K VB upon B whole square into x minus C1 upon K. Now this becomes dt by dx equal to minus 1 by K mu VB upon B whole square into x minus C1. Solving further, we get K into dt by dx equal to mu VB square VB upon B whole square into x minus C1, which gives us Qx equal to mu into VB upon B whole square into x minus C1. Now putting values at x equal to B, we have Qx equal to 0. So it gives us C1 equal to mu VB upon B whole square into B. Now putting these values, we get T equal to minus mu by K into VB upon B whole square into x square upon 2 minus mu VB upon B whole square upon B into x divided by K plus T naught. Now rearranging further, we get T minus T naught equal to mu into VB square upon K into B into x by B minus 1 by 2 x upon B whole square. Now rearranging further, we get T minus T naught equal to mu VB square by K equal to x by B minus 1 by 2 x by B whole square. This is the final equation which we get.